This is a short explanation video for the paper L4acados, Learning-Based Models for Acados Applied to Gaussian Process-Based Predictive Control, published in the 2025 Transactions on Control Systems Technology. Machine learning libraries such as JAX, PyTorch, or TensorFlow, as well as physics simulators such as PyBullet or Mojoko, are powerful tools for deriving accurate models for control systems in various application domains. However, coupling them with established software packages for optimal control, such as Casadi and acados, is generally difficult and often requires tailored implementations. In this work, we bridge this gap by presenting L4acados, which interfaces Python-based dynamics models with acados for high-performance optimal control. Say we are interested in solving the following general optimal control problem as part of a model predictive control strategy. There, we minimize a cost subject to an a priori dynamics model of our system, as well as constraints over a finite prediction horizon. To improve the quality of the predictions, the nominal model f can be augmented with a learning-based residual model g, implemented efficiently in one of the aforementioned software libraries. But how to interface the external libraries with optimal control software based on Casadi? To interface the residual model G, in this work, we consider numerical solutions to this OCP obtained by sequential quadratic programming. Thereby, the nonlinear OCP is approximated by a quadratic program that consists in a quadratic cost approximation, as well as linearized dynamics and inequality constraints. At each SQP iteration, this QP can be efficiently solved for an increment, which is used to update the current estimate of the optimal solution. The only information needed from our dynamics model f is thereby its evaluation at the current estimate, as well as its Jacobians with respect to the states and the control inputs of the system. In L4acados, this is utilized to integrate external learning-based models by modifying the necessary sensitivity information at each iteration. The workflow of L4acados is as follows. The user needs to specify two ingredients. First, a nominal formulation of the optimal control problem in acados, and second, a Python-based residual model. From the nominal OCP, L4acados automatically extracts the SIM solver, which is used to compute the sensitivities of the Casadi model. From the residual model, L4acados obtains the corresponding sensitivities at each SQP iteration. Depending on the library used for the residual model, the computation of the sensitivities can be straightforwardly parallelized to speed up the solver for computationally intensive residual model evaluations. Both sensitivity information are combined at a minimal computational overhead using the acados Python interface. In the following, we will demonstrate the usage of L4acados at the end of zero-order Gaussian process-based MPC, which is a computationally efficient algorithm for uncertainty-aware control using Gaussian process models. For GPMPC, a GPyTorch residual model instance is used, which efficiently evaluates the sensitivities of the GP mean, as well as its covariance based on PyTorch. Additionally, a custom update function is used in acados to propagate the model uncertainty and tighten the constraints accordingly. The algorithm is implemented on hardware using the CRS platform for autonomous miniature racing. The setup is based on a Qualisys motion capture system for state estimation, while the MPC controller is executed on a laptop, transmitting the control commands to the car via Wi-Fi. The racing controller is formulated as a model predictive contouring controller. It uses a kinematic bicycle model for modeling the car dynamics, as well as a simplified Pacheco tire friction model to estimate the tire forces. As the tire friction is very difficult to model in general, it is augmented using a Gaussian process for uncertainty-aware control. Due to the fast dynamics, the MPC controller is required to meet a sampling frequency of 30 Hz. Here you can see the GPMPC with the prior model, without any data. The red line shows the predicted state trajectory. The red ellipsoids show the corresponding probabilistic reachable set approximation. Due to the large open-loop uncertainty prediction, the car drives cautiously and close to the center line. In the second run, the GP model is updated with 400 data points collected in the first run. The resulting uncertainty predictions are significantly smaller, allowing the car to drive closer to the track boundary, leading to faster lap times. Finally, the GPMPC is applied with online learning. Here, a fixed dataset of 100 points is used and updated online with new measurements. This illustrates the potential of GPMPC for cautious online learning, reducing the conservatism in the predictions by updating the system model on the fly. You can find the L4acados software, as well as a link to the full paper on GitHub under the following URL, accessible via the QR code. The full paper additionally contains a benchmark of the computational performance of L4acados, as well as the GPMPC implementation for a lane-changing maneuver with a full-scale autonomous vehicle. Thank you for your attention.